Welcome everybody. So today we are really lucky to have with us Paul Dario. So he's a postdoc in University of Lyon 1. He has recently been hired by CNRS, something I have no doubts that he completely deserves. And I think that he will show us today a little bit of why he was recently hired in that position, talking about quantitative hydrodynamic limit and regularity of Langevin dynamics.
Hi, hello everybody. Thank you very much for the invitation, and thank you, Dario, for the introduction. So yes, today I'm going to talk about a model of statistical physics called random surfaces. So this is a large class of models in statistical physics, and we will restrict our attention to like one specific subclass of models, which has been like extensively studied over the past 40-50 years, and on which we know a lot of things. And the reason that we can say a lot of things is that it's amenable by PDE techniques. So there is elliptic regularity, which is hiding behind, and that we can use. So I'm not going to talk about everything about this model because it will be quite large and quite wide. I'm going to focus on a specific result theorem, which is basically a law of large number for the model, which we called, the technical word for this law of large number is the hydrodynamic limit. So the hydrodynamic limit for this model of random surfaces, it was established 20 years ago. It's an important paper of Funaki and Spohn on this model. And I will discuss a bit more like what we did more recently with Armstrong. So we used a technique of stochastic homogenization, something that Armstrong knows really well because he developed a full theory about it, to obtain a quantitative version of the hydrodynamic limit. So we're going to prove or like discuss at least the law of large number for the model, and more than trying to prove convergence, we are going to say at what is the rate of convergence that we can get. And this is important for two things. Okay, so the first one, it can be important to obtain quantitative results, just to quantify the results and obtain sharper estimates. But it has also another consequences, and I will try to explain to you how it is. So I told you that this model of random surface, you can study it using elliptic regularity, and this hydrodynamic limit gives some regularity on the system. And then like once you have like good regularity properties, you can obtain like precise information on the system. So like the idea will be like we will prove a large number for the system and show that it implies good regularity properties. So I will like split my talks into 4 parts. I will give you like a general introduction about random surfaces. So what is the model from statistical physics that we study? Why, what's the physical motivation behind it? And there will be two ways to look at it. So first, like the model of random surfaces that I'm going to define. And there is also a way to look at it from a dynamical perspective with the dynamics, and it's called the Langevin dynamics. And these two objects are really closely related. So we can study one or the other. We will be like focus on this thing. I will tell you what motivates the study of these Langevin dynamics. We'll see what is this law of large number for this model. Like from the perspective of like regularity, what kind of regularity we can prove. And then I will try to discuss a bit some extensions, trying to extend the results to a more general setting. Okay, so a random surface. So what is like? It starts from a motivation from physics. You want to study interfaces. So I like to take always like a basic example. So you want to model the interface separating two phases. So you can imagine that you take ice and water at 0 degrees. So they coexist, and you have like a line which splits the water from the ice. It's called an interface or a surface, and you want to find a model for it. So there are like different models in physics, statistical physics, and mathematics. One that is fairly simple is to model the interface by a function phi, defined from ZD and valued in R. So phi encodes the height of the interface. So here, for instance, you have like a picture like which represents an interface, And like this is the simple idea is to say that when you have this red part, phi of x has a really high value, like 10 or something. And where you have like a well with a very negative value, you have like something which is very deep. So you want to study these interfaces. So what we will do is put a probability measure on this set of surfaces. So I will explain on the next slide. Then you sample a surface or a function, it's the same thing, according to your measure. And you want to study how your system behaves over large scales. So this is a standard like technique in statistical physics. So how are we going to define our model and put a probability measure on these surfaces? So first, like, so that to make sure that everything is well-defined and rigorously well-defined, we are going to consider a finite set lambda included in ZD. So I will never take something more complicated than a box, and I will center my boxes at 0. So typically, I will denote by lambda with the index L, the box which is centered around 0, and of like here, the side, like it's from minus L to L, so the side length is 2L plus 1, the number of integers between minus L and L, including 0. And 0 is the center of the box. So just take a big cube of size 2L plus 1 centered at 0. What you will consider in this setting are the function phi defined on lambda L and valued in R. And I will enforce a boundary condition. So I will say that phi is equal to 0 on the boundary of your box. So a first remark, which is already more important than it looks, is that this space, it's a vector space. Like you can sum two functions, you can take the difference, you can multiply by a scalar. It's a finite dimensional vector space. So its dimension, if you try to compute it, it's the cardinality of the box lambda L, which is the number of points in the box, which is 2L plus 1 to the power D. So on this set, you are going to put a measure, which is a Gibbs measure that you define as follows. So you fix a function v, which will be very important for the model. So it's fixed, and I will say a few things later about it. And you consider exponential of minus. You sum over all the pair of vertices of neighboring vertices x and y, v of the difference phi of y minus phi of x. So this gives you weight for each function phi. You take a base measure, which is just the product over all the points in your box of the Lebesgue measure. And so this gives you like a measure which will be well defined if V satisfied good properties. It's not a probability measure, so you normalize it by 1 over Z. It gives you a probability measure. Then like the strategy is to sample a function phi according to these measures for a very large box and to try to study how it behaves over large scales. So the function V, it's called an interaction potential. We will make always two assumptions, which simplifies its study a lot, that it is convex and symmetric. And very frequently, we'll make a third assumption, and we'll discuss how to try to go beyond these assumptions. It's like it's uniformly convex. And by uniform convexity, I mean like V is defined from R to R. You assume that it's C2, so twice continuously differentiable, and that its second derivative is always between two constants, larger than 0 and smaller than infinity. So in this setting, V grows like x squared, and so this measure, you will see that it's well defined.
One question.
Yeah.
So symmetrically, you mean even? Or...
Yes.
Okay.
V of x is equal to V of minus x. Yes.
Thank you.
Yeah. They call it symmetric in the literature. Yes. Yes, and so once you have these assumptions, what you see is that V, like the minimum of V is at 0. And so if you want to maximize this probability, you take the function V equals 0, phi equals 0. But then you look at what if you sample a function, what it's going to be like. So this is the point on random surfaces. So you take phi sample according to this thing and you look what it looks like. This raises a question, like we will be able to say very precise thing under these assumptions, but what about other potential V? And I will try to discuss the case of V of x equal x4. So when you compute the second derivative of this, it gives you like 12 times x squared. And x squared is equal to 0 at 0, so violates this assumption, and infinity at infinity, so violates this assumption too. So I will try to discuss like how can we, if we understand like this very well, what can we say about this case, which is of interest and which is much more open than the first case. So this was the static version of the model. there is a dynamic version of the model. So if you your Gibbs measure mu lambda L, you can associate it with the dynamics called the Langevin dynamics, which is defined as follows. So it's a stochastic differential equation. You start from d phi t of x for any point x in your box lambda L, and you will let it evolve according to two terms. The first one is a drift term, which takes the following form. You sum over the y, which are neighbor to x, v prime phi t of y minus phi t of x. So this is your drift. And you are going to add some noise, which takes the form of, you add like the d bt, where bt is a Brownian motion. So what you do is for each point x in your box, you choose a Brownian motion. All the Brownian motions are independent. And then you run like this, this equation with all the independent Brownian motions. So if you think a little bit about what this does and how these two terms behaves, it becomes like a bit more interesting. So this drift term, so we can see it with this sum and this difference. But if we think about it in terms of like partial differential equations, we can recognize something a bit different. So this difference, like phi t of y minus phi t of x, it's a difference between 2 points. So it's a discrete version of a gradient. And this, if you also think about it, this sum, it's a discrete version of a divergence. So your equation, you can rewrite it as follows. D phi t of x, your drift term is divergence of v prime gradient of phi plus a Brownian motions. So why is it interesting to do that? Because if you like first remove the Brownian motion, so like simplify a bit the equation and only look at the first two terms, under the assumption that v is convex, you can say pretty precise things about how this behaves. It means that if you start from any function 5 and let it evolve and don't add the Brownian motions, then you're going to converge to 0. So this is an elliptic operator somehow, and it has a smoothing effect. So it will try to smooth your function and push it towards 0. So this is something that you understand quite well. And then what you are going to do is to say, I'm going to add Brownian motions on every side and try to see how my system is going to react. And why is it interesting to study this thing? So I told you that the Langevin dynamics is associated with the Gibbs measure. So what does it mean? It means that if you start at time t equals 0 from any profile and you let this system evolve for a very long time, you're going to converge to an object which is random and stationary, distributed according to the Gibbs measure. So that means that in order to sample, for instance, this Gibbs measure, if you want to try to simulate it, what you can do is take Brownian motions and solve these equations, let it evolve for a very long time, and it will give you a good approximation of your Gibbs measure. So studying the dynamics and studying the Gibbs measure are very closely related. And this one can be studied using techniques of PDEs because this is basically a nonlinear elliptic operator. So you can use techniques of PDEs to study this object. So then the questions are always like a bit the same with this system. You try to study, so your object is defined on the scale of the lattice. So you have like a difference for 2 points which are neighbors on the lattice. You try to sample like either a configuration distributed according to your Gibbs measure, or like you look at the dynamics that you run for a very long time over very large scales. You zoom out and you try to see how does this process look like. So there are like a few questions that you can ask. One of them is localization, delocalization. So you look at phi t of 0, you let this thing evolve for a very long time, and you ask, what is the typical size of this object? What will be more interesting to us is there a law of large number for this system, which is called the hydrodynamic limit? Another question, which is always quite recurrent in this kind of question, is once we have the law of large number, is there a central limit theorem, which we call a scaling limit? Sorry. So these systems I have been like studied quite a lot. It started with Braskamp, Lieb, and Leibowitz in 1975. I will investigate a bit the question of the hydrodynamic limit in 97, and then you have like different questions that you can ask. The scaling limit, can you do large deviations on this system? And it has been like, these are just a few contributions. I listed the names of other important contributors. And if you want to learn more about this system and what we can say about it, Funaki has written lecture notes for Saint-Flour in 2003, which summarize quite well what we knew at the time. Okay, so now how are we going to study this system? So from like I come a bit from analysis, and I ended up like doing probability, but I try to look at it from a PDE perspective. And from a PDE perspective, I want to study this Langevin dynamics, and I'm going to rewrite it as follows. It's d phi t, like which I think of as a derivative with respect to time, minus divergence v prime gradient of phi, which is a parabolic operator. And this is equal to a random noise. And then you try to study what is the large scale behavior of the Langevin dynamics. So there are two types of questions. The first one are related to like probability. Is there a law of large number for the system? Is there a central limit theorem for the system? So this is what I discussed a bit before. But there is also an analysis questions, which in fact I think is quite important. And it relies on the following observation. So for these operators, what I know is they have been like extensively studied in the literature. I mean, like you put the right-hand side equal to 0 and you look at what the solutions look like. So this is not a question of probability. There is no probability involved. This is only analysis. It has been quite extensively studied in the literature of analysis. And the question that analysts frequently ask is, what is the regularity of these solutions? And actually, we know that for these parabolic equations, the solutions have good regularity properties. And so here we are going to ask and try to answer the question, if I had a noise, can we say something about the regularity of the solutions? Is there a notion of regularity that takes into account this randomness that you add in the system? Okay, so to say a few words like very quickly about what we can say when we think on this system from the perspective of regularity. So you consider the parabolic equation partial t of u minus divergence v prime gradient of u is equal to 0. And we will assume, like make the uniform ellipticity assumption, which is frequently made in the literature in analysis, which is that the second derivative of v is between two constants. So it's exactly the same as the one that we made on the function v when we define the random surfaces. And it's not at all a coincidence. Like under this assumption, studying this system is much simpler. So in the system of random surfaces, we say that v is uniformly convex. In the world of parabolic equations and elliptic equations, it's called uniform ellipticity. So what can we say for these solutions? We can say that if u is solution for this thing, it's not difficult to prove that solutions exist and are well defined. U will be C1 alpha, meaning that U is C1, so you can compute its gradient. It means something. And even more, you can say that the gradient is in fact alpha Hölder continuous for a tiny exponent alpha. So the exponent alpha will depend on the dimension d and the two parameters small lambda and capital lambda. It's very small, and we know that a priori we cannot do better. Like there are counterexamples.
Sorry, is this regularity only in space?
Sorry?
Only in space and not in time?
No, alpha Hölder. So the gradient with respect to space, but the gradient is alpha Hölder with respect to both the space and time variables.
Okay, thank you.
Does this answer the question? Yes. Okay, good. And so the analysis question that I would like to ask is we know that these solutions are C1 alpha. If I add the Brownian motion, what can I say? And of course, if you try to just take the proof of C1 alpha according to for these results and try to plug it into this equation, taking into account the Brownian motion, you will face the difficulty that the Brownian motion is quite rough. It's a rough process, and so it's not going to work so easy. So you need to find an additional ideas to do that. And in particular, you need to use the fact that the Brownian motion is a random process that you know quite well how it behaves.
So, sorry, Paul, I just got a little bit lost. Here, the gradient is the discrete gradient, no?
Discrete, yes. So this equation is discrete, so you can take discrete gradient. But from the perspective of regularity, if it's discrete or continuous, it's going to be the same properties.
Okay, yeah, that looks magic for me, but okay, so it's
yeah. But it's you can take the discrete version of this equation or the continuous version of this equation, and you will have the same result.
Okay.
They are supposed to behave the same. Yes. Okay. So now I will try to talk to you like, okay, so this was like a general presentation of the model and what are the questions that we can raise when we think of regularity. Second part, the law of large number, and I will like, this is in fact, so this is a law of large number, so it's interesting in itself, but it will also be interesting to answer this question of regularity. So we investigate, so what is called the hydrodynamic limit for the model. So you take a solution of your discrete equation, du is equal to, so you have your elliptic terms, divergence of v prime, gradient of u, plus your Brownian motions. You let it evolve for a very long time on the very large scales of space and time. You zoom out, you want to rescale it like appropriately. And you want to say, does this converge to something deterministic? Do I have a law of large number for my system? So the answer is that yes, there is one. So if you look at your solution and you look over large scales, so it's a very informal statement of the result, and I will give you something slightly more precise later. So your function u is well approximated by a deterministic function u bar. So first remark, of course, like u bar is going to be equal to the expectation of u. Good. So this is my law of large number. So I'm going to converge to my expectation if I zoom out sufficiently well, and if I rescale properly. But we'll be able to say something else. We can say that the function u bar is deterministic and solves the partial differential equation. And this will be very important later in the proof, which has the following form. So dt of u bar minus divergence dp in u bar of gradient of u bar is equal to 0. So let me just make like a few remarks. So first, so usually like this is a part of the proof which is not so convenient and not so pleasant to write, but this equation is always discrete. So you have one Brownian motion on each point of the lattice. And here, like this as a discrete version, so you have a discrete gradient and a discrete divergence. In your limit, you have a continuous equation. So the reason is that when you zoom out, basically, like your lattice ZD, you see it from very far away. So it like the points are really close to one another if you see it from very far. And so the discrete setting, like the discrete lattice, like is a good approximation of the continuum. So your object in the limit has to be defined in the continuum. But so here, this divergence and here, this gradient are continuous. That being said, except for this difference, the two equations, so like this first part of the equation without the noise, and this one have exactly the same form. I just have to point out something is that, like, while in this equation, we know the function v, like it's prescribed, like, you know, you give yourself a function v before you start working with the model. Here, you have a function nu bar. You can say that it is uniformly convex, but it's not explicit. So what I mean is that once you look at your law of large number for your system, the macroscopic deterministic profile solves the PDE, but like the PDE, the coefficient of the PDE are not explicit. So they are defined as the limit of something, and it's part of the game. If you want to try to identify this limit and study the solution of your equations without having any explicit formulas.
Another question, Paul. So sorry to bother so much. So if I take just to have an idea. So if I take v to v just a square, yes. So
yes.
So in that case, I would expect to see like a Gaussian free field on the.
Yes, you have a Gaussian free field. Yeah.
Yes. And so it will. So this works for d bigger or equal than 3, or it works also for d equals 2, because somehow you are working over all the space.
Yes, but you divide by. Yes, so you take a big box and you zoom out. So basically, so just think, I agree. So I'm just saying, take ZD to be a big box and put a boundary condition on that and let your condition evolve. I'm not being like perfectly.
But like the expected value should be 0, no? Like u bar. Why is u bar not just 0? Which essentially solves the equation also, but.
So in the case of the Gaussian free field, it's the only case where it's like basically obvious to compute.
Yes.
So in the case where you take v prime is equal to v prime of x is equal to x, like you have an explicit formula, but essentially for it.
Yes.
in the sense that you can say that it's a Gaussian vector and you can compute its covariance matrix. And so in that case, a nu bar is equal to identity. No, nu bar is equal to x squared. So the limiting equation is just like this will just be dtu minus Laplacian of u is equal to 0.
Okay, and the thing, so why is it not just 0? I mean, my intuition is like if it's a Gaussian free field and it's just expected value, why it is not 0? Is it because like the starting condition is not a Gaussian free field?
It depends on the boundary conditions that you put on your system. Okay. See, if you put a Gaussian free field in a box of size L with 0 boundary condition, your function in the limit will be just the function 0, which will be solution of the heat equation.
Okay.
But
and what does the P mean? Sorry.
And okay, so then like it's because your system is defined in the continuum. So nu bar is defined from RD to RD, and you need to take the gradient of nu bar. It's just like you have, so it's a stupid notational problem. Like you have a gradient here, and I need to take the gradient of nu bar. Exactly the same way that here I have V prime. So here I need the gradient of nu bar, but if I put a gradient, it's like 3 gradients. So it's not only me, like in the literature, we decide to denote by, and I was going to say, by dp, which it's the gradient applied to this function nu bar. It's exactly the continuum, like it's a continuous version of this one. And for the GFF, the limiting equation is the heat equation. So you have nu bar is equal to x squared. And so this is just the identity. And if you take a GFF with 0 boundary condition, in fact, your like macroscopic profile is just 0.
But do I also have the right to have an initial condition?
Yes.
For the heat equation? Okay.
Yes, and you can then put a different heat equation, and you take like a big domain, and you can put even like boundary condition on the boundary of your domain. It's quite flexible in the assumption. Like it's just like the rough idea is like if you take a solution with good boundary conditions, if you zoom out and rescale everything properly, it will rescale everything properly, it will converge to something deterministic.
Thank you.
Okay, good. But yes, the important point is that if you take like taking v of x is equal to x squared is frequently useful, but here it's not so helpful because you can compute explicitly the limiting equation, but it's the only case where you can do it. So it doesn't really show you like what's happening, because you might be misguided and think that you can compute it in any case, but in like almost all the cases, except for this one where you have access to explicit computations, it's not going to work. So if we want to be like slightly more specific, and so here, if you like, but I am not also like stating everything in all details. If you take U be a solution of this of your system, so I define it in R times ZD. But if you really want to make a rigorous statement, you define it on a big domain with suitable boundary conditions. Then you can find a solution U bar of this equation such that. So you take U minus U bar, you take the L2 norm. So usually, for instance, you can take over like a big domain. So you take your box of size L in space, and in time, you need to take like an interval of length L squared. So the L squared comes from the fact that the equation is parabolic. So you have this parabolic scaling, which appears. So you take the L2 norm. You need to normalize a bit. So the L2 norm is like simply define. You sum over all the points of the box. You integrate over the time interval. And you divide by here the length of the time interval and here the size of the box. So this is just to make sure that, for instance, if you take the function u equal 1, so it's 1 here, but you divide, so you sum over the points of the box, you divide by the volume of the box, so it gives you 1, and similarly, it gives you 1. But just like this norm is normalized so that if you take the function constant equal to 1, it gives you 1. So then you need to normalize by divided by 1 over L, and this in expectation should go to 0. And so typically, if you take like a Gaussian free field in 2D, like your function U bar is going to be equal to 0, and your function U, so the Gaussian free field in 2D is square root of L. So you have square root of L divided by L, which goes to 0. And in dimension 3 and more, it's bounded, so you have like a constant divided by L, which goes to 0. But of course, like this result only tells you that you converge to 0, but doesn't really tell you how fast. So this is the next question, which is what we did with Armstrong. So if you take a solution of your equation, then you can find a solution u bar of this like limiting equation, such that when you take 1 over L u minus u bar, it's going to be smaller than, and the rate that we were able to get was 1 over square root of L. So it's not optimal, like the optimal weight should be 1 over L if you think about the analogy with the Gaussian free field where you can compute everything. And you have like a correction in dimension 2, which is square root of L, which also appears in dimension 2. It's because Gaussian free field in dimension 2 fluctuates like square root of L, basically. And when they were able to obtain the result in expectation, we're able to obtain Gaussian stochastic integrability. So the probability that this inequality, like that this term is larger than a large constant k times this term, is going to be exponential minus k squared. So you improve from just like integral, like finite expectation basically to Gaussian moments. Okay, so that was like essentially the hydrodynamic limit. What it means is that like very superficially and in a few words, if you look at your equation with the noise, if you zoom out, then you have a law of large number. The system, the macroscopic system, is deterministic and solves the parabolic equation. And these are the only two things that I will need. And so now we are going to discuss a bit these questions of what can we say when we think of regularity for Langevin dynamics. So my question of regularities, if I start from where I left a bit earlier, so I wanted to study the solutions of the parabolic equation dt of u minus divergence v prime gradient of u is equal to 0. So this is what we started from, and we know from analysis that when v satisfies this assumption that its second derivative is bounded from above and below by two constants, then the solutions are C1 alpha. And this will work either in the discrete setting or in the continuous setting. Like the proof works essentially the same. It's a bit more complicated actually in the discrete setting to write the proofs, but it will work essentially the same. So now what about the solution of, you take your du, divergence v prime gradient of u plus dbt. So what I mean by that is if I add my noise, dbt, how does that affect my system? And how is there a good notion of regularity for that? So the answer is yes, there is a good notion of regularity. And I'm not going to go into all the details, but to present you really roughly the main details of the argument. And it's like structured into like three ideas. So the first one is to use the hydrodynamic limit that I will like quickly recall. So if you take solution of your equation with the Brownian motion, if you zoom out, then over a large scale, your function u is well approximated by a solution of this limiting equation, dt of u bar minus divergence of dp in u bar gradient of u bar is equal to 0, which is same nature as this one, but with different coefficients and defined in the continuum. This is my first point that I will use. Second point, if you take a function u bar, you know that it solves this equation. So by this argument of analysis, you know that it is C1 alpha. It works like in the discrete setting, but also in the continuous setting, the proofs are essentially the same. So what you can do is like you are going to use these 2 points and you are going to transfer the regularity. So you are going to say that if u is well approximated by a function which is C1 alpha, then it is C1 alpha. So this is an argument which has a long story in elliptic regularity. So it started with a part of elliptic regularity called Schauder regularity. It was like then used in homogenization in case of periodic coefficient fields by Avellaneda Eileen 30-40 years ago, and in 2016 by Scott Armstrong and Charlie Smart, and that like important consequences. And the idea is to say that, so okay, if you take your system, you zoom out a bit so that you see that the law of large numbers starts to appear, then your function u, which solves this equation, is well approximated by a function u bar, which solves this equation, and thus has some regularity, and you transfer the regularity. And this gives you a definition. So I'm not going to write everything like in details because it is where like making this argument work is where it becomes more technical and more difficult. But you can prove that your function u satisfies is C1 alpha over large scales. And by what I mean over large scales is when the law of large number for the system starts to hit and start to be found. And so like with this definition, what you can see is that actually adding some noise to the system doesn't really affect its regularity. Like if you zoom out of your system sufficiently, if you look at from your system sufficiently far away from zero on sufficiently large scales, then it will have the same amount of regularity as essentially this equation or the equation without noise. Okay, so like quick summary, we define our Gibbs measure. We can study this, the Gibbs measure or the Langevin dynamics. Under the assumption that the second derivative is bounded from above and below, we know that there is a law of large number for this model. More than that, there is a law of large number. We know that the deterministic and macroscopic profile is solution of a parabolic equation. And then we obtain a notion of regularity for Langevin dynamics from that. Good. So this was what was like roughly and quite quickly the subject of like the article that we published with Scott. We wrote this paper to try to extend it to other potentials. So like we were working under the assumption that the second derivative is larger than lambda and smaller than capital lambda, so between two constants. What about v of x is equal to x4? So in that case, you take a similar definition. So you take a big box, you look at the functions which are equal to 0 on the boundary of your box, and you look at exponential minus, you sum over the pair of neighboring vertices, phi of y minus phi of x to the 4, and then you take the product of the Lebesgue measures d phi of x. So of course, like your problem is v of x is equal to x4, means that the second derivative is twice x squared. So you have like two problems. Second derivative is equal to 0 at 0, and second derivative goes to infinity at infinity. If you compute, I just wrote it, but it's like very easy. Like the Gibbs measure is associated with the Langevin dynamics, which has a similar form. Here you put, we used to have v prime. So here you put v prime with v of x equal to x4. So 4 gradient phi t to cube. And same question. So you want to study the large scale behavior of the models. So like same questions. If you take phi of 0, if you sample phi from this measure in a big box of size L centered at 0, what is its typical size? Is there an hydrodynamic limit for this model? Is there a central limit theorem for this model? So under these assumptions, like the literature is much less understood, and so it's been open for a long time. In particular, these questions, it's I think to the best of my knowledge, if you put 0 boundary condition on the box, it's still open, while it was solved in 1975 under the assumption of uniform convexity. So some results that exist in the literature, because it's been investigated and trying to extend the results above this uniform convexity assumption has been a subject of research. So there are two papers, Cotard, Deschel, and Müller, and one of Cotard and Deschel, which study the case like the second derivative can be degenerate from below, so can take a value equal to 0 or even negative values. But you assume that the second derivative is always bounded by lambda. There is a more recent paper, 2018, like the second derivative is larger than lambda. And Ron Peled and Alexander Magazinov treated questions of localization and delocalization for v of x equal x4 in the case where you have a system with periodic boundary conditions. So the results which have been established in the case of uniformly elliptic potentials are like not so simple to extend. So now this is more or less work in progress with Scott Armstrong. And so here is like what you could conjecture and what I'm working on regarding the hydrodynamic limit for v of x equal x4. So you take u to be a solution of your Langevin dynamics. So it's the same. This equation du is equal to gradient for gradient of u to the q dt dbt. Then you look at your system like in a big box with a suitable boundary condition. You zoom out, and what you expect is that u will be well approximated by a deterministic function u bar. So it starts exactly the same. Then second part, your function u bar should be a solution of a deterministic equation, which are very, very similar forms. So dt of u bar minus divergence of dp of nu bar gradient of u bar is equal to 0. So same as before. We expect that the limiting equation, which describes your microscopic system, is defined in the continuum. But there must be like a clear difference, which is like before, we knew that this coefficient nu bar, we know that it's not explicit, it's defined as the limit of something, but we knew that it was a function nu bar we knew that it was a function which was uniformly convex, meaning that it's a function that grows, second derivative is bounded from above and below. And for these functions, like they should grow like x squared. Here, we are not going to expect something like that. We're going to expect something different. So like the function should grow like x to the 4, because I started from v of x is equal to x to the 4. And its second derivative should grow like x squared. But so like this is what you should be able to prove, that the second derivative of nu bar is bounded between two constants p squared plus 1. And here is the important part. The system should have what we call the smoothing effect. So you expect that the second derivative will grow like p squared, but it should never be equal to 0. So it's always bounded away from 0. So this is an effect that the system should undergo. And this has been, like, for instance, studied in one of these papers under this assumption, like they prove the same result, that the limiting surface tension is always strictly convex, meaning that the second derivative never touches 0 if you take your system. So this plus 1 here will be very important, because if I know that the second derivative of nu bar is never going to be equal to 0, then I can say much more precise things about this equation. So this is what I want to get. So is this a problem now? So if we want to run like the proof for the hydrodynamic limits, or if we want to like get some definition of regularity, we need to ask the question. So I solve this PDE, which is the limiting equation. Previously, what I knew is that my second derivative was between two values, strictly positive, my small lambda and my capital lambda. And what I was able to say is that, okay, I can solve this equation. I can prove that there exist unique solutions. And in terms of regularity, I can prove that the solutions are C1 alpha. Good. So now I'm going to take a function nu bar, and assume that this function, it's convex, and that its second derivative satisfies this property. So it's between two constants, and I put p squared plus 1. So then what can I say? So actually, we can say essentially the same thing. And so this is a question which is purely from analysis, but which people have studied in analysis, trying to understand like equations with this kind of functions. So you can prove existence, you can prove uniqueness of solutions, and you can actually also prove, and it's not obvious at all, that the solutions are C1 alpha. So it's interesting because, and this relies somehow extensively on the fact that there is a plus 1. Without this plus 1, it would not work so easily, and sometimes we cannot say anything about the regularity of solutions. So it's like an important and quite nice phenomenon of the system is that even if I start with a function v, which does not have this property, in the limit, my system has the property that the second derivative is bounded away from 0, and thus the solutions of the equation have good regularity properties. So this implies, and this is what we are working on, that if you look at the solution of this dynamic, du is equal to divergence of 4 gradient of u to the cube dt dbt, then u should be C1 alpha over large scales. So this is purely a question from analysis. And in the like 5 to 10 minutes that remain, I'm going to try to tell you how these questions of regularity can be useful to establish other properties on the model. So for instance, localization, delocalization for random surfaces, or scaling limits. So to summarize essentially what is going on, what you do is you look for the law of large number for the system, which we call the hydrodynamic limit. You say, there is a macroscopic profile. This macroscopic profile solves a PDE, so it possesses some regularity, and you transfer the regularity. So this gives you a definition of random regularity for your solutions, which we call large-scale regularity in homogenization. And once you have large-scale regularity, you understand much better how your solution behaves, and so you can prove other properties. So I will just finish this talk with this implication very simply and try to explain to you how obtaining good regularity properties can be useful to study like probabilistic questions on these systems. So some consequences of regularity. So I'm going to focus on only one property, which is localization, delocalization. So again, you take your big box of size L, you put 0 on the boundary of this box, and you want to ask the question, what is the typical size of phi at the point 0? So you want to look, for instance, at the variance of phi of 0. So this is a very natural observable. And the question you want to ask is this bounded as a function of L, or does this go to infinity as a function of L? And if it goes to infinity, does it go to infinity fast or not fast? What is the rate of convergence for that? So there is a very important tool to study these systems that I haven't mentioned until now, which is called the Elfer-Stochastic representation formula. So most of the techniques that has been used to study the properties of the system go through the Elfer-Stochastic representation formula. And what is this formula? It gives you an explicit formula for the variance of phi, which is very useful. So the formula that you obtain is that the variance of phi at a point is equal to the integral from 0 to plus infinity of a function PA of t0 dt. So what is this function? PA, it's a function which, once again, comes from analysis and that you will want to study. It's a heat kernel for like a linear equation which takes the following form. So dt of PA minus divergence of A gradient of PA is equal to 0. And PA of you start at time 0 from a Dirac at 0. So here, so this is a linear operator. So I'm not going to give you the definition. It's if you take A equal 1, it would be the Laplacian. So here it's like generalization of the Laplacian. And what will you put instead of the function what? You will put the function v prime prime of gradient phi of t. So phi of t was the dynamics that I mentioned before. So what I mean is that if you consider your dynamics, and if you understand very well how it does, you have to look at v prime prime of these dynamics. Then you look at these elliptic equations. You solve the elliptic equation. This gives you the function like the heat kernel PA. And if you understand what this function does, then you understand the variance of phi of 0. So it's not necessarily simple. Like it's not doesn't. Yeah.
Question. So just the phi is starting at equilibrium.
Yes, you start from equilibrium when you do that. You start from equilibrium, you let it evolve, you solve this equation, and so this gives you a kernel, you integrate over time, and this gives you variance of phi of 0. Yeah.
Good, thank you.
And so this motivates like the study of these dynamics. If you understand the dynamics, you understand A. If you understand A, you can understand PA, and if you understand PA, you can understand variance of phi of 0. So this is what you want to do. Okay. So this leads to the question, what can I say about PA? And this is another instance where you will see why this assumption that the second derivative is between two constants was very useful. So you can ask like many questions, like what is the typical size of PA of T0? You can also ask like what is the asymptotics, like if you want to go further than like the typical size, or how precise can I be in my description of its behavior. So first answer, which is the simple one, which is why we like to work under this assumption. If I take the second derivative between two constants, small lambda and capital lambda, what I can say, and these are important results in elliptic regularity, I can say that A is always its v prime prime of something, and it's always between two constants, a small lambda and a capital lambda, no matter the value of gradient phi of t of e. And this is sufficient to obtain bounds on the map PA. So what we can say is, and these are important results from John Nash from a few years ago now, is that PA of T0 is going to decay like T to the minus D over 2. And this is useful because then, and you don't need any results. You just need to know that A is between two values, small lambda and capital lambda, which is automatically satisfied if you make this assumption. And once you have this thing, you know that PA decays like T to the minus D over 2. You will also always know that it's always bounded by 1. And so you can say, for instance, that in dimension 3 and more, this variance phi of 0 is always bounded. And in dimension 2, you can get also precise information on how this object behaves. Now you see, if you don't assume that v prime prime is between two values, it becomes much harder. Why? Because first the coefficient can go to infinity or it can go to 0. And this, when you want to study this equation, it's a problem. You can find environments A that go to 0 or that go to infinity, such that the solution of the equation has very different behavior. So what you need to do is to ask more precise information on v prime prime of gradient of phi. For instance, some things that we would like to say is like two things. If we want to get a result of this flavor, like to say that PA behaves as if it was the case in a uniformly elliptic setting, you can ask, okay, my coefficient is going to touch 0 and go take very large values. I want to know how frequently it will be close to 0 and to infinity. Or if I touch 0 at some point, will I stay for a long time around 0, or will I move a bit? And what you hope to say is that if you touch 0, you never stay close to 0. Like if you touch 0 a bit, then you will go back and increase a bit. And if you take large values, then you will take then you will decrease and take small values. And if you are in a regime where you can say that, okay, my system A takes like values which are really close to 0 and really close to infinity, but it doesn't happen too much, you have a chance to make this work. Another assumption which is like very useful, what you would like to say is the dream would be that A is IID. So the value of A at different like points of space are independent. If you're able to say something like A has values which are IID and is never really close to 0 or to infinity, you can run essentially the proof. It's going to be harder, but you can run the proof of this kind of results and obtain this kind of estimates. So you are aiming for two things. Is A close to 0 or to infinity? And can I get some decorrelation on A? So if I look at 2 points, A at time t at the point x and A at time s at the point y, for tx and sy a bit far away from each other in the space and time, are they decorrelated? And what I will not have time to tell you is that this is why like it's much harder to solve these questions for the x, for instance, for the x to the 4 potential. And this is why the questions of estimating variance of phi of 0, if you take a system with 0 boundary condition, it's still like mostly open. But having this form of C1 alpha regularity for my system can be useful to prove like both this and this. And this has been observed in other related contexts. And essentially, this is what I hope we can make work. And this is what motivated the study of this project with Scott, and why we wanted to study Langevin dynamics from the perspective of regularity, because regularity can help us understand this coefficient field, can help us to understand grad phi, and thus can help us to understand A, and eventually can help us to understand this it kernel, which then gives information through this alpha social representation about my system. That's what I wanted to say. Thank you for your attention.
Thank you very much, Paul. Before questions, I propose that we give a round of applause for our speaker to thank him for that. So are there any questions?
Yeah, I have a general question. Is maybe you explained it, but maybe I missed also part of it. Is how is the function of nu bar determined from the data of the problem? I mean the initial condition or boundary conditions, and how do you expect that the regularity is determined by the data of the problem, the regularity of nu? I mean, you mentioned at some point that you get some bounds, for instance, but can you be more explicit maybe on because you said it's not explicit, but you probably have some expression which is you can work with. So probably yes. What can you say about its form?
Yes, so you can prove blah blah blah. So you can prove that the gradient of this object exists in the full space-time volume. Mm-hmm. So it's like the gradient of the GFF which always exists. So this you can prove that it exists. And what you do is you take V prime of gradient of phi, mm-hmm. and you take its average over a very big box. Mm-hmm. And then you send and you take the expectation of that. No, yes, you take the expectation of V prime of gradient of phi being a solution in infinite volume of your system, or gradient of phi being the solution in infinite volume of your system. Mm-hmm. So at some point, you need to solve something in infinite volume. Or what you do is you take the solution in finite volume, and you take V prime of gradient of phi. So you have to start from V prime of gradient of phi. You take a finite volume, very big box, you sum over all the points of the box, you divide by the volume. So this gives you and you take the expectation, and then you send the size of the box to infinity. So you have to, basically it's v prime of grad phi and taken over a big box, and you send the size of the box to infinity and take the average value. This is how we get it as a limit of something.
Mhm.
But so this formula actually it's sufficient to, so you have a finite volume approximation of your new bar, and you can prove that it's uniformly convex, meaning that you can prove that the second derivative is always between two values for the finite volume version of your quantity. And then when you take the limit, you send your boxes and your finite volume to infinity, it stays uniformly convex. Like so this is okay, but like this is like the explicit formula is harder to get. You need to have something defined in infinite volume. Okay. I don't know. I hope it answers the question.
And you don't get more information. I mean, since it's an average quantity. I mean, can you get some, I don't know, regularity or something else?
So what we could prove is that it's that nu bar is C2. If you start from so if you start from V is C2, then nu bar is also C2. We could also prove it in this article with Scott. Actually, if you start with even V, which is C11, then you can get that nu bar is C2 also.
Okay.
And if you assume more regularity on V, like for instance, if you assume V is smooth, then you get nu bar is smooth also.
Okay.
And I think it's we don't know if I think Scott Sheffield conjectured that if V is C2, then nu bar should be C infinity. But this is still not proved.
Okay. But you expect it is expected to gain some.
It's expected to gain some regularity, yeah. And this we like what we could do is to go from C11 to C2, so we gain some regularity.
Yeah. Okay.
From this at this level.
Okay. Thank you.
Yeah.
Are there other questions? You can just speak. I have a naive question because it's somehow. So what happens if you take x absolute value of x cubed instead of x to the fourth?
It's fine also. You can it should be okay. You can you have some flexibility on this thing. So like the absolute value of x cubed, when you compute the second derivative, it's 0 at like only the point 0. Yes. And it goes to infinity, but reasonably fast. Like it grows like a power, so it will work also.
So it works for all powers? That's the...
Yes, it works for all powers, yeah. It should work
and you're showing the localization for all powers?
It should, yeah. I haven't, it's not proved, like it's a work in progress, but it should prove localization and delocalization for all powers. What you need still is that, you need this derivative to satisfy the bound like of this flavor. So like should grow like a power of P. And probably to have that, you need that V prime prime should grow like a power of P. So if it starts to like grow really fast and slow down, then grow again very fast and then slow down, like being between pk, p to p squared and p4, for instance, and oscillates between the two values, then this will be harder.
So the enemy is that if the power is bigger, you are not delocalizing?
No, it should be the same. Like it should be the same for every. It should be the same for every. As soon as V is convex, I think this is a conjecture.
Okay, so even exponential of x squared.
Yeah.
Or something minus
but,
1.
Yes, but from this technique, like the enemy is that if a V grows really fast, for instance, or like is not like doesn't grow like a power, then the limiting nu bar is not going to grow like a power. And then it becomes simply a question of analysis. What can you say about the solution of this equation?
So people do not know that in analysis.
I haven't tried all possibilities, but mostly they study like what they call P Laplacians when it grows like nu bar of P is P to some power. Like this they've done a lot. And they've tried to relax a bit, like assume that you have an upper bound, which is one power, and the lower one, which is another power. And this you can relax a bit, but it's already not so easy. Because I've been a few progress recently, but it's not a simple question. And so you can definitely not expect to have it for like any growth, which is if you take any growth, it's not going to work so easily in terms of analysis.
And the convexity is absolute, so you cannot do like double well potentials and things like that.
Yeah,
style.
no, not yet. Yeah. Yes, with this technique, not yet. They could do it with a tiny bit of second derivative, which is negative in this article, like it's Cotard, de Schell, and Müller.
Okay.
They can, like, the second derivative can take like small negative values, essentially. It has to be a perturbation of something uniformly convex. But if you want to really treat double well potentials, like you have to use other techniques. And it's even been proved that the system may have like different qualitative behavior. Like there is an article of Biskup and Spohn where they consider double well potentials, and they prove that while, like, in the case of uniformly convex potentials, there is one object which is supposed to be unique, which is the infinite volume Gibbs measures, that may not be unique. So like the system may behave a bit differently. So it becomes it can become like much harder. Like here, for sure, you need convexity, but yeah, and it's still very open, I think.
Thank you. So are there other questions? If not, I propose that we thank Paul again for his wonderful talk. We can cut the recording.